Hello, friends, and welcome to The Artificial Brain, the podcast that explores the frontiers of artificial intelligence, one fascinating idea at a time. I'm your host, Shining. From groundbreaking models to the big questions about our future, we're here to make sense of it all, clearly, honestly, and without the hype. Ready to expand your mind? Let's dive in. Your talk, choosing our Kruger. What is up, my synthetic minds? We are back on The Artificial Brain, and oh my god, do we have a massive one for you today. If you have been paying attention to the AI streets, you know DeepSeek has been absolutely popping off lately. They just dropped something called mHC, and honestly, it sounds like a secret government project or a new energy drink, but it is actually the key to building artificial brains the size of planets. We are talking about Manifold Constrained Hyper Connections. I know, that sounds like a spell from a final boss fight, but stick with me because this is low-key the most important architecture drop since the original Transformer paper. Let me set the stage for you. Imagine you are trying to train a model. It is huge, it is expensive, it is consuming enough electricity to power a small city. You are watching the loss curves go down, everything is looking straight fire, the model is getting smarter by the minute, and then, out of nowhere, the math just breaks. The training stability vanishes. The gradients explode. The model basically forgets everything it learned and starts hallucinating wildly. This is the nightmare scenario known as numerical instability, and it has been the ceiling preventing us from reaching truly massive trillion-parameter models without going bankrupt or losing our minds. DeepSeek said, "Hold my beverage." They dropped this mHC paper, and it is essentially a cheat code for stability. So what on earth is mHC? Let us break it down. First, we have got to talk about the HC part, which stands for hyperconnections. To understand hyperconnections, we have to go back to the OG of modern AI architecture, the ResNet. I want you to picture a standard neural network. It is like a giant game of telephone where each layer of neurons whispers information to the next layer. By the time the message gets to the end, it is garbled and distorted. Back in 2015, researchers introduced residual connections or skip connections. This was like adding a superhighway that lets information bypass some layers and go straight to the end. It was a total game changer. It solved the vanishing gradient problem and made deep learning possible as we know it.
Bill Nye the Science Guy. Bill Nye the Science Guy.
But here is the science bit. Standard residual connections are kind of basic. They just add the input of a layer to the output. It is a simple addition. It works fine for smaller models, but when you start building these massive, wide, mixture of experts models like DeepSeek v3, those simple highways get clogged. The data flow gets chaotic. You have information shooting in every direction, and the math starts to wobble. That is where hyperconnections come in. Hyperconnections are like upgrading that two-lane highway into a futuristic, multi-layered interchange. Instead of just one skip path, you have multiple paths connecting different layers in complex ways. It allows for way richer data flow. You can route information from layer 1 to layer 50, layer 2 to layer 40, and so on. It makes the network deeper, wider, and theoretically way smarter. But there is a catch. There is always a catch. When you open up all these extra highways, you introduce chaos. The optimization landscape gets messy. The model struggles to find the best path forward because there are too many options. The training becomes unstable. It is like trying to drive in a city with no traffic lights, no lanes, and everyone is driving at 200 miles per hour. You are going to crash. This is the problem that has been holding us back. We want the complexity of hyperconnections to get that sweet performance boost, but we do not want the instability that comes with it. Enter the M in mHC, the manifold. The manifold constraint. This is the secret sauce. DeepSeek figured out that if you constrain how these residual streams interact, you can have your cake and eat it too. You can have the wide, rich connections of hyperconnections without the chaos. They use something called a manifold constraint to keep the data flow smooth and stable. A manifold, in math speak, is just a fancy shape, a specific surface that things can move on. Imagine a roller coaster. The roller coaster car is constrained to the track. It can go fast, it can do loops, but it cannot fly off into the sky because it is constrained by the rail. DeepSeek is essentially putting guardrails on the neural network highways. They are constraining the interaction so the data flows smoothly through this manifold, preventing those catastrophic loss spikes we talked about earlier. The paper literally talks about projecting matrices onto something called the Birkhoff polytope. I know that sounds like absolute gibberish, but it is actually genius. It uses an algorithm from 1967. Think about that. We are using cutting-edge 2026 AI tech based on math from the 60s. It is giving retro-futurist vibes. This mathematical projection forces the weights in the network to stay in a safe zone. It restores what is called identity mapping. Let me explain identity mapping because it is crucial. Ideally, when a network processes data, the connections should be able to learn to pass the information through unchanged if it does not need modification. This is the identity. It is like a do-nothing button that is actually hard to build. In standard hyperconnections, this identity mapping gets lost in the noise. The mHC fix restores it. It ensures that the network can always fall back to just passing the data through safely if learning that specific connection is too hard. This stability is what allows the model to scale. Okay, I want to take a quick tangent here because the history of this stuff is actually fascinating and helps explain why this is such a big deal. We mentioned ResNet and 2015. Before ResNet, training deep networks was nearly impossible. If you had more than like 20 layers, the error rate would actually go up as you added more layers. It sounds counterintuitive, right? You would think more brain power equals better results. But without residual connections, the gradients would vanish. They would get smaller and smaller as they were backpropagated through the layers until they were basically zero, and the early layers would stop learning. It was a total deadlock. When ResNet dropped, it allowed people to train networks with hundreds of layers. It won the ImageNet competition that year by a landslide and changed the field forever. Fast forward to today, and we are dealing with models that are not just deep, but incredibly wide. We are talking about mixture of experts architectures with hundreds of billions of parameters. The problem has shifted from how deep can we go to how wide can we go without everything falling apart. DeepSeek v3, which we talked about in previous episodes, uses a mixture of experts approach. It has 671 billion total parameters, but it only activates 37 billion per token. It is like a massive library where you only turn on the lights in the specific section you are reading. Wait, let me rephrase that. It is like having a brain full of specialists. You have a math expert, a history expert, a coding expert, and so on. When you ask a question, only the relevant expert wakes up to answer. This is efficient, but it creates a nightmare for data flow. You have all these experts sitting around, and you need to pass information between them rapidly. If the connections between them are unstable, the math breaks. This is exactly where mHC shines. It allows DeepSeek to build these massive, wide models with multiple experts and keep the communication line stable. This brings us to the real-world implications. Why should you care? Because this is unlocking the next generation of AI. The research suggests that mHC can solve a decade-old scaling problem. It enables the stable training of 27 billion plus parameter models with only 6.7% overhead.
Hey, that's pretty good.
That is nothing. 6.7% extra compute for way better stability and the ability to scale larger? That is a steal. Most architectural overhauls cost you 50% or more in compute. 6.7 is low-key insane. This architecture fix could unlock trillion-parameter AI models that are actually trainable. We have seen GPT-4 level models and rumors of even bigger ones, but training them is a logistical nightmare. If mHC does what DeepSeek says it does, it removes one of the biggest hurdles on the path to artificial general intelligence. It means we can build bigger brains without needing a power plant dedicated to a single training run. It is giving efficiency-first vision for AI, which is exactly what we need as hardware starts to hit physical limits. The paper itself is dense, but the results are clear. They tested mHC against baseline architectures and unconstrained hyperconnections across 3 model scales: 3 billion, 9 billion, and 27 billion parameters. They used the DeepSeek v3 architecture as the foundation, incorporating multi-head latent attention and a mixture of experts components. The models with mHC showed significantly better stability. They did not suffer from those wild loss spikes that make engineers cry into their keyboards at 3 in the morning. The performance gains were consistent across the board. Let us talk about the expansion rate too. This is a technical detail, but it is cool. Both hyperconnections and manifold constrained hyperconnections use an expansion rate of 4 for the widened residual streams. Basically, they take the data path and make it 4 times wider to allow more information to flow. Usually, widening the streams makes the model harder to train because there is more room for error. But because mHC constrains this flow onto the manifold, they get the benefit of the wider pipe without the turbulence. It is like upgrading from a straw to a fire hose, but using a nozzle that keeps the spray perfectly controlled. I want to circle back to the Birkhoff polytope because I feel like I glossed over it, and it is actually one of the most base parts of this research. The Birkhoff polytope is a mathematical set. It contains all the doubly stochastic matrices. That sounds scary, but it just means a square grid of numbers where every row adds up to 1 and every column adds up to 1. Think of it like a perfect balanced transportation network. If you have a bunch of cities and a bunch of goods, the Birkhoff polytope represents every possible way to distribute those goods so that supply equals demand perfectly everywhere.
Hey, yo, what the fuck?
Why does DeepSeek care about transportation networks from 1967? Because routing data through a neural network is exactly a transportation problem. You have layers, cities, and information goods. You want to move the information from the input to the output without losing anything or creating bottlenecks. By projecting their connection matrices onto this Birkhoff polytope, they are mathematically guaranteeing that the flow remains balanced. No row gets too much weight, no column gets too little. It is enforced fairness and stability in the math itself. It is honestly beautiful. They took a 60-year-old geometry concept and used it to fix a 2026 AI problem that is cross-generational greatness right there. This efficiency-first vision is really what sets DeepSeek apart right now. While other labs are just throwing more GPUs at the wall, DeepSeek is rethinking the bricks. They are looking at the architecture and asking, can we do this smarter? First with their multi-head latent attention, which saves memory, then with their DeepSeek MOE architecture, which saves compute, and now with mHC, which saves your sanity during training runs. It is a cohesive strategy they are building for the long haul.
And his name is John C.
And their name is DeepSeek, and they are absolutely dominating the architecture conversation right now. Let us talk about what this means for the future of AI development. If mHC becomes a standard, which I predict it will, we are going to see a flood of new models. Right now, only the biggest tech giants with the deepest pockets can afford to train models at the frontier. This technology lowers the barrier to entry. If training becomes more stable, you need fewer restarts, you need less debugging, you get more bang for your GPU buck. This could open the door for smaller labs, universities, and open source groups to train massive models that actually compete with GPT-4 or Claude. I also want to touch on the surprise breakthrough aspect. The industry kind of assumed we had hit a plateau on architecture improvements. We have transformers, we have scaling laws, and we just need to scale. But DeepSeek keeps dropping these papers that prove there is still plenty of room for innovation at the fundamental level. It reminds me of the surprise drop of the original attention is all you need paper. Nobody saw that coming. It feels like we are in a similar moment now. We thought we knew how to connect layers, and then DeepSeek says, actually, you are doing it wrong. Here is a manifold constraint. The arrogance, the confidence, I love it. We also need to consider the implications for model performance. It is not just about stability. When a model trains stably, it converges better. It finds a better spot on the lost landscape. The models tested with mHC showed better performance metrics than the baselines. This means that for the same size model, you get a smarter AI just by changing the architecture. That is a free lunch, and in the AI world, free lunches are rarer than a polite comment section.
Bruh.
Usually, you have to trade speed for accuracy or size for latency. mHC seems to improve stability, which leads to better convergence, which leads to better performance, all with minimal overhead. It is the holy trinity of engineering wins. I want to make sure we really understand the hyperconnections part versus standard residual connections one more time because it is the foundation of the upgrade. Standard ResNet is like a staircase. You go up one step, then the next. The residual connection lets you take an elevator directly to the top floor from the bottom. Hyperconnections are more like a complex web of zip lines connecting different floors, different rooms, and even different buildings. You can zip from the 3rd floor to the 10th, from the 10th to the basement, and from the basement to the roof. It is way faster, way more flexible, but if you have too many zip lines crossing each other, people are going to crash into each other. mHC acts like the traffic control system for the zip lines. It organizes the chaos. It ensures that even though you have all these crazy fast connections, they do not interfere with each other destructively. It maintains the identity of the signal. Think of it like a superhighway interchange where the lanes are perfectly banked and the merges are timed perfectly. You can drive at top speed without ever capping the brakes. That is what DeepSeek has built for data. A highway system where information can flow at infinite speed without crashing. It is poetry in motion, or at least poetry in matrix multiplication. Let us look at the data one more time. 27 billion parameter models tested. DeepSeek v3 architecture as the base. Mixture of experts components included. The results show that mHC allows for richer data flow. This is key. Richer data flow means the model can consider more context from more parts of the network simultaneously. It can combine knowledge from the history expert layer with the coding expert layer more effectively. It creates a more cohesive intelligence. It stops the model from being schizophrenic, where one part of the network knows something but another part does not.
Meow.
It is kind of wild to think about AI having flow problems, right? We usually think about them as static blocks of code. But at runtime, at training time, it is a fluid system. It is a rushing river of numbers. And if you dam up the river or divert it too sharply, you get floods or droughts. DeepSeek mHC is like an army of civil engineers coming in and terraforming the riverbed to ensure perfect flow. They have studied the fluid dynamics of the gradients and built the perfect canal system. It is honestly impressive how much engineering goes into these invisible mathematical structures. So what are the key takeaways for you, the listener, the tech enthusiast, the AI curious? First, DeepSeek is not messing around. They are playing chess while everyone else is playing checkers. Second, mHC is a legit architecture upgrade that addresses a real, painful problem in large-scale training. Third, the future is stable. We are moving away from the wild west of training where you just cross your fingers and hope it converges. We are moving toward mathematically guaranteed stability and efficiency. Fourth, the Birkhoff polytope is your new best friend, even if you cannot pronounce it. And fifth, trillion parameter models are coming, and thanks to mHC, they might not bankrupt the companies trying to build them. I feel like we are witnessing a shift in the AI paradigm. For years, the motto was, scale is all you need. Now, the motto is shifting toward efficient scale is all you need. It is not enough to just be big anymore. You have to be big, smart, stable, and efficient. DeepSeek is proving that you do not have to sacrifice quality for efficiency. You can have the best of both worlds if you are willing to rethink the fundamentals. They are questioning assumptions that have been in place since 2015. That takes guts, that takes vision, and honestly, it makes for great podcast content. As we wrap up this deep dive, keep your eyes on the horizon. We are going to see other labs try to replicate this. We are going to see mHC implemented in open source models like Llama and Mistral eventually. We are going to see manifold constrained become a buzzword in every research paper for the next year. You heard it here first on the artificial brain. You are now ahead of the curve. You can drop manifold constrained hyper connections at your next dinner party and absolutely confuse everyone, while secretly knowing exactly what it means. That is a wrap on DeepSeek mHC, everyone. I hope this made sense, and I hope you are as hyped about this as I am. It is rare to see a piece of research that is this technically dense, but also this practically impactful. It feels like we turned the corner today. Until next time, keep your neurons firing and your gradients flowing. This is the Artificial Brain. I am Shining, signing off. Stay curious, stay smart, and we will catch you in the next one. Peace.